today's topic is the Fourier series. Today's topic is the Fourier series. Okay, before starting Fourier series, the basic elements of Fourier series. First concept is periodic function. We know that fx is said to be periodic if and only if f of x plus t is fx, where t is the period of fx. Example: sin x, fx equal to sin x is a periodic function. In period 2 pi, because sin x plus 2 pi is sin x. Okay, now we will discuss this definition in detail. Suppose my function is defined like that. Fx is such that f of x plus 1 is fx with the property that f at 0 is 0, f at 0.1 is 1, f at 0.2 is 2, and f at 0.9 is 9, and f at 1 is again 0. So therefore, what will be f at 1.1? It is again 1, because f of 1 plus 0.1 is same as f at, what should you write? 0.1, and which is 1. It means that if I wanted to draw the graph of this is 0 and this is 1. So at these points I will be drawing the graph. So it is like that, it is like that, it is like that, it is like that, and like that. So the graph somewhat like that. So between 1 and 2 the graph will be somewhat like that. So it means this graph will repeating like that, this way, and so on. So it means if the graph repeats after a certain interval, and then we say that fx is a periodic function. Now, suppose I have defined my function like that. Another example. Our next concept is the periodic extensions of the function. Periodic extension of function. Periodic extension of the functions. It is also somewhat interesting one. If I define my fx as, suppose it is defined like that. It is minus 2 when x is lying between minus pi and 0, and it is plus 2 when x is greater than 0 and pi. Now if we see this graph, this is minus 2, this is minus pi, rather than this minus pi, and this is pi, this is plus 2, and this is minus 2. So here is the graph is like that. These are the point of discontinuities, and like that. Now what is the periodic extension of this graph. Now, between pi to 2 pi, this graph will be somewhat like that, and between pi to 2 pi to 3 pi, this graph will be somewhat like that. So it is nothing but the periodic extension of the function, and the length of this interval is 2 pi, that is length of minus pi to pi. So therefore we will take period as 2. That is the length of the interval. Actually what we did, we have taken the graph up to this interval and we are repeating this graph over the whole real line. So therefore the period will be only 2 pi. So this is what we have to do in the Fourier series. We will take the periodic extension of the function, even if the function is not periodic. Now the second concept of the Fourier series is the even and odd function. Even function. By definition, the function is even if f of minus x is fx for every x belongs to the domain. For example, suppose my function is fx is equal to x square, then what will happen? F at minus x is same as minus x whole square, which is x square, so which is same as fx. If you see that the image of minus 1 is same as f at 1, image of minus 2 is same as f at 2. It means if the graph is somewhat like that in this region, then the mirror image, if you take this y-axis as a mirror, then this graph will be repeating like that. So a even function has a symmetry with respect to y-axis. So now I am writing down the property of even functions. Properties of even functions. Now therefore removing this in order to move ahead. Properties of even function. Graph of fx is symmetrical with respect to y-axis. This is property number 1. And property number 2, we have already studied that integral minus a to a fx dx will be twice of 0 to a fx dx because of the area property. So in fact we will use only these two properties and then we will extend this idea. Now what is an odd function? Next definition is odd function. Odd function. If f of minus x is equal to minus fx for every x belongs to the domain, then fx is odd. For example, fx is equal to x, then f of minus x is minus x, which is minus fx. Now, important property. You will find that f at 1 is 1. What is f at minus 1? Minus 1. So if we see, we try to draw this graph at 1 and at minus 1, 1, minus 1. Point is here. Then the corresponding point in the opposite quadrant. Similarly, if point is here, then point is here. Here, here. So this graph will be like that. So it has a symmetry about opposite quadrant. That is symmetrical in opposite quadrant. Or symmetry about origin. About origin. Another example we can consider of this. I am removing this for timing. For example, if I take fx equal to x cube, if I take its derivative, then it will be 3x square. Now see that. Clearly this passes through the origin and this derivative is greater than 0 over the interval 0 to infinity, so it is a strictly increasing function like that. But it is an odd function, so therefore the graph is like that. So this is fx equal to x cube. So it is a symmetry about origin, so therefore it is an odd function. And f of minus x is equal to minus x cube, that is minus fx, so therefore it is odd function. Okay. Now properties of odd function. Properties of odd function. Properties. I am writing collectively properties. Integral minus a to a fx dx is twice of 0 to a fx dx if f of minus x is fx, and it is 0 when f of minus x is minus fx. It is like that. This is property number 1. If f of minus x is fx, then symmetry about y-axis. And if f of minus x is equal to minus fx, then symmetry about origin. Number 3, product of two odd function is even, and product of one odd and another even is odd, and product of two even function is even. So these properties we are going to use in the Fourier series, these properties. Now, some important things that I am going to use in the Fourier series, some general values you have to keep in your mind. Please note that sin n pi is 0 when n belongs to the integers, and cos n pi is minus 1 to the power n, that n is same. Second is a very important formula that is known as the Bernoulli's formula. What this formula is saying that integral u v dx is equal to u v1 minus u dash v2 plus u double dash v3 minus u triple dash v4 and so on, where v1 is integral of v dx, v2 is integral of v1 dx. So in general, if I write vn, vn is integral of vn minus 1 dx, and u dash stands for du by dx, u double dash stands for, and so on. Actually this formula is really important to do the calculation in faster manner. For example, suppose it is applicable if one of the function is polynomial, that is integral, suppose x square sin x, let it be u and let it be v, then it will be x square. What is the integral of sin x? Minus cos x minus derivative of this 2x. What is the integral of minus cos x? Minus sin x. Integral of derivative of this 2, and then minus sin x is cos x plus c. So you can calculate in one line only this integral. Similarly, x square e to the power x dx, if I take this as u, this as v, then it will be x square e to the power x minus 2x e to the power x, then plus 2 e to the power x plus c, like that. Now, I am defining the concept of Fourier series. Fourier series. Concept of Fourier series. Just try to understand the concept. So So in order to have a Fourier series, we need to have some condition. Let fx be any function defined on a to a plus 2l, or it can be this, where a and l are any constant. A and l are any constant. Number 1, take f of x plus 2l is equal to fx. This is nothing but the length of the interval. Length of this interval. Number 2, fx should be piecewise continuous. That is fx can have finite number of discontinuities on a to a plus 2. Number 3, fx should have finite number of maximum minimum and minimum on a to a plus 2. These properties are known as the collectively. These properties are known as the Dirichlet condition. These conditions should exist. Then we can talk about the Fourier series of the function. Now let us understand that suppose a function satisfies all these 3 conditions, then how to write the Fourier series over this interval. Look at here. We used to write the Fourier series of the function as fx is equal to a0 by 2 plus summation n varies from 1 to infinity an cos n pi x by l plus bn sin n pi x by l, where a naught is equal to 1 by l integral a to a plus 2l fx dx, and an is 1 by l integral a to a plus 2l fx into cos n pi x by l dx, and bn is 1 by l integral a to a plus 2l fx into sin n pi x by l dx. We will find the value of a naught, an and bn, substitute here, and that will be the Fourier series of the function. We define Fourier series also in other words that it is a series which contains sine and cosine, is known as the Fourier series of the function. Okay, we can write this also as, if we little bit, this can be further written like that, 2n pi x by 2l. Please understand why I am writing. This 2 will get cancelled with this, and this can be further written like this, sine 2n pi x by 2l. This 2l is the length of the interval, and this can be further written like this, 2 upon 2l, and this can be also written like that. This formula further can be written like that, an equal to 2 upon 2 by l a to a plus 2l fx cos 2n pi x by 2l dx. Similarly, this can be written like that, bn is equal to 2 upon 2l a to a plus 2l fx into sine 2n pi x by 2n dx. So now I think you should understand the concept that why I have written this way. And this can be written this way also. Now I will do one example based on this so that you can feel the concept. Suppose the problem is fx is equal to x square over the interval base. Clearly it is continuous and it is a piecewise continuous, not defined at minus pi and pi. Now what I am going to do, now length of the interval is 2 pi. So I have to do f of x plus 2 pi is equal to fx. So I think now you should understand this concept. The graph of this should be like that. So what I will do, I will draw this graph like that, and then later on what I will do here, it is 2 pi and it is further 3 pi and 4 pi. So the graph of this will be further will be equal to if we reconsider it somewhat like that and so on. This graph. This is what we call periodic extension. Periodic extension. Now use the formula. So then how will write the Fourier series of this? Fx will be equal to a0 by 2 summation an cos 2n pi x by 2l. 2l is the length of the interval, which is 2 pi plus bn sine 2n pi x by 2 pi, which is length of the interval. This will get cancelled with this. This will get cancelled with this. So fx will be a0 by 2 summation an cos nx plus bn sine nx. It is like that. Okay, now without loss of generality, I am moving ahead. So therefore, a0 will be equal to 2 upon 2 pi from where to where? Minus pi to pi. Fx is x square dx. It will get cancelled with this. This is 1 by pi. Now since it is an even function, so I can write 2 by pi, 0 to pi, which is 2 by pi. X cube by 3 is 0 to pi. 2 upon pi. If you simplify it, pi cube by 3 minus 0. This will cancel with this. So it is 2 pi square by 3. So I am writing in the side that a0 is 2 pi square by 3. So we have found the a0. Later on I will substitute here. Now I will find an. An will be similarly like that. 1 that is 2 upon 2 pi from where to where? Minus pi to pi. Fx into cos 2n pi x upon length of the interval is 2 pi. So an will be equal to 1 by pi. Fx is x square cos nx dx. It is even. It is even. So net result is even. So 2 by pi, 0 to pi, x square into cos nx dx. It is like that. Now I am removing this also. Please note that. What will be the value of this integral? 2 by pi. Take this as u and this as v and use Bernoulli. It will be x square into sine nx by n 0 to pi minus derivative of this 2x into minus cos nx by n square 0 to pi then plus 2 into minus sine nx by n cube 0 to pi. Now you know that sine n pi is 0 and 0 at 0 is also 0. So it is 0 minus 0. Then minus minus plus, so it will be 2 pi by n square outside. It will be cos n pi minus 0 because it is multiplied by this. Plus it will be entirely 0, 0 minus 0. Now it is nothing but 2 by pi this will get cancelled with this. So it is 4 times of minus 1 to the power n by n square. So your an is 4 times of minus 1 to the power n by n square. It is it. Okay. So these are the calculation of an. Now I am going to find bn. Now what is bn? Accordingly, we can write bn also by using the same concept, 1 by pi from minus pi to pi x square into sine nx dx. It is even. It is odd function. So the net result is 0 because integral minus a to a fx dx is 0 if fx is odd. So therefore bn is 0. So therefore what will be the Fourier series of the function? Fx will be equal to a0 by 2 plus summation an cos nx plus bn sin nx. A0, substitute the value of a0. What is a0? 2 pi square by, so it will be only pi square by 3 plus summation. What is an? 4 times of minus 1 to the power n by n square into cos nx, and bn is 0. If I expand it, then what I will get? Pi square by 3. When n is 1, it will be only minus 4 cos x. When n is 2, plus 4 by 2 square into cos 2x, minus 4 by 3 square into cos 3x, and so on. It is like that. So it is the Fourier series of the function. Now I am giving you one more example. Suppose the function is like that. Fx is equal to, say, x over the interval and it is say it is like that, minus x other than this, and it is x. Now I want to draw the graph of this function. This is pi and this is minus pi. Note this important thing. Now in this interval x will be negative, so the graph of the function will be like that, although it is discontinuous.